This is the second part of our discussion of L'Hopital's rule. In this video, we're going to cover the power forms that are indeterminate. 1 to the infinity, 0 to the 0th power, and infinity to the 0th power. In order to be able to solve these and convert them to a basic form, we'll first have to convert them into the 0 times infinity form. The only way we can do that is to get the power out of the power. And that means a natural log. I'm going to share my screen with you now so we can get started. In order to convert to 0 over 0 or infinity over infinity from the power forms, we first have to go through the form 0 times infinity. To do that, we're going to have to apply the natural log to our function. Then we can use the property of natural logs that allows us to pull the power on the answer part to the front and multiply by it. In other words, when we're looking at it, we're going to use the property that the natural log of x to the 8th power is a times the natural log of x. This gets it out of the power and down to the line. 1 of a and the natural log of x is going to be 0, and the other one will be infinity. This will give us the 0 times infinity form. Never ever move natural log. So in order to convert this to 0 over 0 or infinity over infinity, we'll have to divide by the reciprocal of a, 1 over a. Now let's talk about what we're doing. The natural log, no matter whether it's the 0 or infinity part, always stays put in the numerator. It's always the original power that got pulled to the front, whose reciprocal we divide by. Now, keep in mind that applying the natural log to the function has changed it, which means we've changed the limit. So we have to undo it. Now, how do you undo a natural log? You have to exponentiate it with the exponential function, e to the x. E to the x and natural log of x are 1-to-1 inverses. Much like adding 5 and subtracting 5 are inverses of one another. They undo each other and get you back to the original value. So if we take the natural log and then we take that result and take e to that power, we have undone taking the natural log. Now this works because of one of the properties of exponentials. Namely, e to the natural log of x is equal to x. In fact, the natural log of e to the x is x2, but that's not the property we need. We need the one that says if you take the natural log of something and you exponentiate it, you haven't changed it at all. In other words, we're going to take a function whose limit is one of the 3 power forms, and we're, instead of evaluating the limit of f of x as x approaches a, we'll evaluate the limit of e to the power natural log of the function. Now, again, because e is a constant, e is about 2.7182818284559, etc. It does not affect the limit. The limit depends only on the variable x, and e is a constant. So we can actually pull the limit into the power, meaning that instead of taking the limit of e to the natural log of the function, we can raise e to the limit of the natural log of the function. And this will enable us to convert it into one of the 2 basic forms. Let's take a look at this example, which I've worked out for you, so that we can see what the steps are. Converting a power form is a lot more work than the previous forms, with the possible exception of infinity minus infinity. The algebra is complicated, and you do have to be very careful to always leave natural log in the numerator. Let's take a look at this limit of 1 plus x to the 1 over x power as x approaches 0. 1 plus 0 would become a 1, and 1 divided by 0 would approach infinity. So we have the indeterminate form, 1 to the infinite power. Now that we know we have one of those power indeterminate forms, we have to apply the natural logarithm function so we can get the 1 over x out of the power and down to the line. However, to undo that, we exponentiate it. We take e to the natural log of 1 plus x to the 1 over x power. Then we pull the limit inside the power. This gives us the limit of the natural log of 1 plus x raised to the 1 over x power. Next, we use that property of logarithms that will allow us to pull the power 1 over x in front of the natural log. So we get 1 over x times the natural log of 1 plus x. The next thing we need to do is reevaluate. We've done something algebraic. We need to reevaluate to see what indeterminate form we have. You should expect 0 times infinity. As x approaches 0, 1 over 0 becomes infinity. And the natural log of 1 plus 0 is the natural log of 1, which is 0. We have infinity times 0, which we know is an indeterminate form. We never, ever move natural log. So we're going to have to divide by the reciprocal of 1 over x, which I worked out in complex form, but let's face it, the reciprocal of 1 over x is x. So we end up with e to the power of the limit of natural log of 1 plus x, all divided by x. Now we have a fraction form, so we need to reevaluate again. We again substitute 0 for x in the revised form to see if we have a basic form. The natural log of 1 plus 0 is again going to give us 0. And in the denominator, we simply have x, which is 0. This means that we have e to the 0 over 0, which is a basic indeterminate form. Because we have a basic indeterminate form, we can apply L'Hopital's rule. In the next step, we apply L'Hopital's rule, taking care to put L'H over the step. The derivative of natural log is 1 over u du dx. And the derivative of x is just 1. After we have applied L'Hopital's rule and simplified, we again substitute the value of the limit into the function, which gives us e to the first power, or e. This means that in the function, as x is approaching 0, the y value is approaching Euler's number e. In fact, this form is considered to be another one of the definitions for Euler's number e. Let's now look at example 17. We'll work this one together, and then I'll let you try 18 and 19 on your own. Let's take a look at 17 now. When we look at 17, the first thing we need to do is substitute into the limit. This gives me 1 plus 4 times 0, all raised to the 3 divided by 0 power. This leads to 1 to the infinity, which I know is a power indeterminate form. So the next thing I'm going to do is I'm going to take the limit as x approaches 0 of e to the natural log of 1 plus 4x all to the 3 over x. Again, e is a constant, so I can pull the limit into the power. At the same time, I can pull the power 3 divided by x to the front of the natural log using natural log properties. This gives me 3 over x times the natural log of 1 plus 4x. I've done something, so I'm going to check again. 3 over x gives me 3 over 0, which I know will go to infinity, times the natural log of 1 plus 4 times 0, which I know will go to 0. This gives me the form infinity times 0, which I was expecting. In this case, because the factor is 3 over x, the simplest thing to do is simply slide the x underneath the natural log. Note that 3 is a constant, which can actually come out of the limit. Limit of a constant times the function is the constant times the limit of the function. Let's go ahead and rewrite it now. This gives me e to the 3 times the limit as x approaches 0 of the natural log of that expression, all divided by the variable. Now I need to reevaluate because I have a fraction. When I reevaluate this time, I have the natural log of 1 plus 0, which goes to 0 over 0, which is a basic form. Now I can apply L'Hopital's rule. I leave the e alone. I'm only applying L'Hopital's rule inside the limit, not in the e part. This gives me 3 times the limit of the derivative of natural log, which is 1 over the expression times the derivative of the expression. The derivative of the variable is simply 1. Now I need to simplify what I have so that I can find the limit value. This is going to give me 4 divided by 1 plus 4x. When I substitute 0 in, I get e to the 3 times 4 over 1 plus 4 times 0, which gives me e to the 3 times 4, or e to the 12th. That is the value that the y is approaching as x is approaching 0. Let's now look at example 18. In example 18, we have a tower function, x to the x. In this case, x is approaching 0. When we substitute, we get 0 to the 0, which is a power indeterminate form. We know we have to take the natural log to pull the power x to the front, but to undo it, we have to exponentiate. Go ahead and pause the video, work it out, then turn the video back on so we can discuss. Let's see how you did. Again, when I substituted, I got the power indeterminate form 0 to the 0th power. I applied the natural log and exponentiated so that I could get the power x down to the line. I pulled the limit inside the power since the base e is a constant. This gave me the form x natural log of x, which when I substituted 0, gave me 0 times the natural log of 0. But I know as it approaches 0, it goes to negative infinity. This is the 0 times infinity form. Next, I have to convert that into a fraction form. I never move natural log. So I took the reciprocal of x, 1 over x, and divided by it. That gave me the limit as x approaches 0 of natural log of x divided by 1 over x. I rewrote the 1 over x in its power form, x to the negative 1. to make it easier to apply L'Hopital's rule. Notice that the natural log of 0 again approaches negative infinity, but 1 over x also is going to approach infinity as x approaches 0. This gives me a basic form of infinity over infinity. Next, I apply L'Hopital's rule. When I apply L'Hopital's rule, I get a rather complicated algebraic expression. Make sure that you use a lot of space and write large so you won't make careless mistakes. Go ahead and take several steps to work it out rather than trying to do it in your head. You do it in your head, you tend to make mistakes. Everyone does, me included. This became 1 over x over negative 1 over x squared. And I took the reciprocal of the denominator fraction and multiplied by it. One of the x's canceled, and I got the limit of negative x as x approaches 0, which is 0. But I had to exponentiate, so this is actually e to the 0th power, which gives me 1. We have one more example to work, which is example 19. In example 19, I'm going to let you do it all on your own. This is a trig function raised to a trig function power. It is going to be a power indeterminate form. Give it a shot and then come back so we can compare. Let's take a look at how to solve this last example of the power forms. Again, when I substitute, I get sine of 0 to the tangent of 0, which is 0 to the 0th power, a power indeterminate form. I know that I have to take the natural log to bring the tangent of x to the line, and then I have to exponentiate to undo having taken the natural log. So I apply the natural log, undo it by exponentiating. This brings the tangent of x down to the line to multiply by natural log of sine. I can pull the limit inside the power because the base e is a constant. Since I have changed the format, I need to reevaluate. Tangent of 0 gives me 0. Sine of 0 is 0, but natural log approaches negative infinity as it gets close to 0. This gives me a 0 times negative infinity, which is an indeterminate form. Then I need to rewrite it in fraction form. We never move natural log. I leave the natural log of sine x in the numerator, and I divide by the reciprocal of tangent, 1 over tangent. But that's actually the definition of cotangent. So I replaced 1 over tangent with cotangent to make applying the L'Hopital's rule simpler. Now that I have converted the form again, I need to reevaluate to see if I can apply L'Hopital's rule yet. Again, the numerator approaches negative infinity, and this time I get 1 over 0 in the denominator, which also approaches infinity. I have infinity over infinity, so I can apply L'Hopital's rule. When I take the derivative of natural log, I get 1 over u times the derivative of u. In the denominator, I take the derivative of cotangent. Then I simplified by rewriting 1 over cosecant squared as negative sine squared. I got some cancellation with 1 factor of sine x, which gave me the power negative cosine x sine x. Then I substituted what the limit was approaching, and I got negative 1 times 0, which is 0, which tells me that the limit is approaching the y value of 1. Now we're going to take a look at a slightly different theorem. This theorem is called the relative growth theorem, and it will help you to find limits at infinity and negative infinity. Let's go take a look. You'll be happy to hear that this one is much simpler to apply. And in fact, there's, well, really no work. It all happens in your head. We've said that there are different sizes of infinity, and there are, but we've not said exactly what that means and how to know when you have a different size of infinity. How do I know that an exponential, e to the x, grows faster than a natural log of x? And is it on an order of magnitude larger? In fact, it's on the order of several magnitudes larger. As we're going to see, we're going to use a double less than symbol to indicate not only a change in the size of infinity, but the magnitude of it. For example, we know that the functions natural log of x, x cubed, and e to the x all go to positive infinity as x goes to positive infinity. They don't get there at the same rate. In fact, x cubed goes to infinity on an order of magnitude faster than natural log of x. And e to the x goes on an order of magnitude faster than x cubed. This is going to affect the value of limits such as x cubed over e to the x. Because e to the x gets to infinity so much faster than x cubed, it drives the limit to 0. Let's take a look at the representation of the relative growth rates of various types of functions. In the list below, where it says algebraic functions, this includes polynomials, power functions, any kind of root or radical, and rational functions. Those are all algebraic. Natural log of x is the slowest growing function that we have that does in fact go to infinity. When you think about the graph of natural log, it is very slow to get to infinity, but it never goes horizontal. It does go to positive infinity, just very slowly. If you multiply natural log of x by some algebraic function, it grows on an order of magnitude larger than natural log of x, and it overpowers it. Algebraic functions by themselves would overpower any product of natural log with an algebraic. And an algebraic function times any kind of exponential, base e or base 5, is going to outgrow any strictly algebraic function. And the exponentials will outgrow the product of an algebraic and an exponential, like x e to the x. Factorials are something that you will experience more when you get into calculus 2. They basically give you the product of all the integer values between the number and 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. These grow incredibly fast. They overpower any exponential function and grow on an order of magnitude larger. The last class of functions are the tower functions, such as x to the x. When you have some kind of expression of x to the x power, this grows faster than any other type of function that we have. I want to show you a picture of what these look like when we get them growing. Let me share my screen with you so that you can see it better. You can see that I have graphed some of the basic types of functions, but in order to see how one outgrows another, I had to change the scale. The x-axis, we're only going from 0 to 8. And on the y-axis, we're going from 0 to 1,000. Notice that the tower function, x to the x, pulls away from the others that I've graphed just after 3. The exponential pulls away somewhere around 5 or 5.5. graph of e to the x takes a little longer to go up, but notice it does not go up at the same rate as the factorial or the tower function. X cubed is graphed here. You know how fast it goes up when you're looking at a normal scale, but look how slow it grows compared to these others. And the last one that's graphed is natural log of x, which we know looks like this and does go up forever, but it looks horizontal because it grows so incredibly slowly. This is what we mean by an order of magnitude. At some point, tower functions outgrow all the others. And as x goes to infinity, that's what matters. Let's now look at our last examples. We want to use what we've just learned about the relative growth rates of functions to write down the value of these end behavior limits without actually computing anything. And the first limit, as x goes to infinity, we have an algebraic x cubed divided by an exponential e to the x. The x grows on an order of magnitude faster, so it gets to infinity much sooner, which drives the value of the limit to 0. I know, it's great, isn't it? Let's look at the next one. This is the limit as x approaches infinity of the exponential e to the x divided by x cubed. This time, the faster growing function is in the numerator, so it pulls the whole thing to infinity. What about the limit of x divided by natural log of x? X is just the identity function, y equal x with slope of 1, but it grows on an order of magnitude larger than natural log of x. So it overpowers natural log of x and pulls the whole thing to infinity. In the next one, we have natural log of x divided by x natural log of 4x plus 1. Notice that we have an algebraic function x multiplied by a natural log that grows on an order of magnitude larger than natural log by itself, which pulls the denominator to infinity, which drives the limit down to 0. Our last example is the exponential divided by the tower function, x to the power of x. That tower function grows so much more rapidly than any exponential that as x goes to infinity, it blows up faster and drives the entire fraction down to 0. I hope that you've enjoyed learning L'Hopital's rule. It really is a magical technique, and it is very useful and something that you'll see quite often in the future. Our last section that we're going to cover out of chapter 4 is going to be on antiderivatives. We are nearly ready to start integration. I'll join you for the next video.